An extreme close-up of feathers from a bird with an uncanny ability to hold water while it flies could inspire the next generation of absorbent materials. With high-resolution microscopes and 3D technology, researchers at Johns Hopkins University and the Massachusetts Institute of Technology captured an unprecedented view of feathers from the desert-dwelling sand grouse, showcasing the singular architecture of the feathers and revealing for the first time how they can hold so much water. It's fascinating to see how nature managed to create structures so perfectly efficient to take in and hold water, said co-author Jochen Mueller of Johns Hopkins. From an engineering perspective, we think the findings could lead to new bio-inspired creations. The U.S. National Science Foundation-supported work is published in the Royal Society Interface. Mueller and MIT engineer Lorna Gibson expect their findings will underpin future engineering designs requiring controlled absorption, secure retention, and easy release of liquids. Possible applications include the design of netting for collecting and retaining water from fog and dew in desert regions, and a water bottle designed to prevent annoying swinging and sloshing. Sand grouse found in African deserts typically nest about 20 miles from watering holes to stay safe from predators. To get water home to thirsty chicks, the adult males perform one of nature's best examples of gathering water and flying home with it. The feat is made even more extraordinary considering the sand grouse is holding about 15% of its body weight in water and keeping most of it safe during a roughly 40 mph flight home that takes about a half hour. Male sand grouse are the only birds known to hold water like this. Their specially adapted belly feathers are the key. Researchers first documented these extraordinary belly feathers more than 50 years ago. But here, with modern technology, the team finally demonstrated how the feathers work. Mueller and Gibson zeroed in on the microstructure of the belly feathers using scanning electron microscopy, microcomputed tomography, light microscopy, and 3D videography, looking closely at the shafts, each just a fraction of the width of a human hair, and the tinier individual barbules. The scientists magnified the feathers, observing them both dry and wet. Then, in a move as delicate as it was crucial, the dry feathers were dunked in water, pulled out, then resubmerged just like a sand grouse at a watering hole. Mueller described the individual feather structure as magnificent, with components optimized in several ways to hold and retain water, including the way they bend, how the barbules form protective tent-like clusters when wet, and how tubular structures in each barbule capture water. Individual feathers held the water through a forest of barbules near the shaft, working with the curled barbules near the tip that acted almost like caps. The team also computationally modeled the water intake of the feathers.